सिग्मा बॉन्ड और पाई बॉन्ड किया था हमने लास्ट में. ठीक, let's continue further. Chemical bonding lecture 6. Continue with sigma bond and pi bond. An important point related to sigma bond is sigma bond in general is stronger than a pi bond. दिखाया मैंने already दिखाया pi bond is much weaker than a sigma bond. We have already written that. Another important point related to sigma bond and pi bond is we'll see the application of this point in the study of isomerism chapter. Write this point. When two atoms are bonded by a pi bond, atoms cannot be rotated about the internuclear axis. About the internuclear axis. Example, when atoms are bonded by a pi bond is formed due to lateral overlap. Pi bond is formed due to lateral overlap. So this is the internuclear axis. If you fix one atom and rotate the other atom, if you fix one atom and rotate one atom and rotate the other atom, ऐसे कर लो, बोल सकते हैं fix the left and right atom, rotate this. On rotating, the orientation of p orbitals will also change along with the. We are rotating along the internuclear axis. The left wala atom to as it is रह गया. It is the atom on the right that undergoes a rotation. Okay. Atom on the right undergoes a rotation along with when it rotates, the orientation of p orbital also changes. The orientation of p orbitals also changes. Now they can no longer overlap. They can no longer overlap. It results in they cannot no longer overlap. That means bond will be broken. So during rotation across a pi bond, when atoms are rotated about a pi bond, the pi bond is broken. Without breaking a pi bond, rotation cannot be done. This is what we mean by atoms cannot be rotated about the internuclear axis when atoms are bonded by a pi bond. When atoms are bonded by a pi bond, atoms cannot be rotated about the internuclear axis because rotation results in change in orientation of the p orbitals, which results in breaking of the pi bond. Without breaking the pi bond, atoms cannot be rotated about the internuclear axis. ठीक है, आ रहा है समझ में? जब रोटेट करेंगे तो ये p orbitals का ओरिएंटेशन चेंज हो जाएगा, ठीक है, and the orientation when it changes, the overlap will break. There will be no more any overlap between the two orbitals. ठीक? So it will result in breaking of the bond. We will write this point. When an atom is rotated, the orientation of p orbital also changes. Resulting in breaking of the pi bond. Across a pi bond, rotation is restricted. Across a pi bond, rotation is restricted. It's an important point. We'll talk about application of this point in organic chemistry and isomerism. Similarly, when atoms are bonded by sigma bond, there is no such restricted rotation across a sigma bond. There is no such restricted rotation across a sigma bond. Atoms bonded by a sigma bond. Okay. When we'll rotate the atom along the internuclear axis, the p orbital along the internuclear axis remains along the internuclear axis. Okay. The rotation along the internuclear axis does not result in any change in the orientation of that p orbital which is along the internuclear axis. ठीक है, तो अगर इस एक्सिस के अबाउट ऐसे रोटेट करेंगे, it does not change the pi bond, it does not change the sigma bond. The sigma bond remains intact. Okay, during this rotation, during the rotation along the internuclear axis, there is no change in the axial overlap. Okay, so rotation about internuclear axis does not affect the axial overlap. Hence, sigma bond remains intact. It does not affect sigma bond. We'll see its application when we study about geometrical isomerism and conformational isomerism. Not in tautomerism. The application of this restricted rotation, free rotation, is there in geometrical isomerism and conformational isomerism. Across a pi bond, rotation is restricted. We say that across a sigma bond, free rotation is possible. We'll write this point. Across a sigma bond, free rotation is possible. Isomerism will study in the just at the around completion of 11th, I think October or November, may will start with organic chemistry. And in the organic chemistry, first chapter is nomenclature, second chapter is GOC, third chapter is isomerism. I think around March, around February, maybe January, February. Depends on how early we start organic. Across a sigma bond, free rotation is possible. We were talking about types of overlap, and types of overlap on the basis of direction of overlap we have done. Another classification of types of overlap will do next week. The basis of phase of overlapping orbitals. Wait a second. Types of overlap on the basis of phase of overlapping orbitals. सबसे पहले पॉजिटिव ओवरलैप, orbitals overlap in the same phase. Example, positive phase overlaps with positive phase, negative phase overlaps with negative phase. Overlapping takes place in the same phase. Positive with positive, negative with negative. These are all examples of positive overlap. You can have positive overlap between an S and a P orbital. This is also an example of positive. ठीक है? प्रीवियस पेज जल्दी से देख लो एक बार. Virok is there in the meeting. You want to join again? Okay. Next we'll study about negative overlap. ये नोट कर लो जल्दी से. After we finish with chemical bonding ना, organic कभी भी start कर सकते हैं. क्योंकि before chemical bonding is difficult to start organic chemistry, but after chemical bonding हम कभी भी organic chemistry start कर सकते हैं. ठीक है? तो इसके बाद अभी thermodynamics खत्म हो नहीं हो कोई मतलब नहीं है. Ideally we should start with organic once we finish with chemical bonding. तो chemical bonding finish होने के बाद दो ट्रैक स्टार्ट हो जाएंगे. Next. negative overlap. Orbitals overlap in opposite phases. This is an example of negative overlap, positive phase overlap with negative phase. Positive phase with negative phase. These are examples of negative overlap. There is another overlap that we define as or classify as zero overlap. Some orbitals are oriented such that there cannot be any overlap between them, however close the atoms come to each other. In such case, we say that it's a zero overlap. Orbitals are oriented such that there cannot be any overlap between them. However close the atoms get to each other. This is called zero overlap. So, example of zero overlap, there cannot be a lateral overlap between S and P orbital. The case of zero overlap. At this point, cannot be a lateral overlap, sidewise overlap. S and P orbitals. Some other examples of zero overlap can be two p orbitals which are perpendicular to each other cannot overlap. Y orbital and the px orbital. There cannot be any overlap between y and px orbital. This is also a case of zero. एक्चुअल में only positive overlap actually occurs and results in bond formation. Results. कुछ एग्जांपल्स देखो. सपोज करो एक्स एक्सिस को इंटरन्यूक्लियर एक्सिस ले लिया. Then Ex plus Px give sigma bond. Perpendicular to x-axis will give pi bond. Py plus Py will give pi bond. Pz plus Pz will give pi bond. S plus Px will give sigma bond. S plus Py, S plus Pz will give zero overlap. Similarly, Px plus Py, Py plus Pz is also zero overlap. आ रहा समझ में? My voice is low. वॉल्यूम तो मैक्सिमम कर रखा है मैंने. बाकी लोगों को भी लो आ रहा है क्या? आर्यन को लो आ रहा है? प्रीवियस पेज देख लो जल्दी से. Let me check. Is it better or same? Fine. ये समझा क्या? If x-axis is the internuclear axis, then Px will give axial overlap resulting in a sigma bond. Py will give lateral overlap resulting in a pi bond. Pz will also give lateral overlap resulting in a pi bond. Px and S will give sigma bond because x-axis is the internuclear axis. There will be no lateral overlap between S and P. So S and Py, S and Pz will give zero overlap. Perpendicular p orbitals will also give zero overlap. So Px Py is zero overlap. Py Pz is also zero overlap. ठीक है? आ रहा है समझ में? देखो, when we have negative overlap, the positive phase mixes with a negative phase, there will be cancellation. The amplitude will be cancelled out. तो वेव फंक्शन की वैल्यू वहां पे जीरो आ जाएगी. वेव फंक्शन की वैल्यू जीरो आ जाएगी, तो प्रोबेबिलिटी विल बी लो. And for bond formation, we need to have high probability of finding electron between the two nucleus. The probability of finding electron should increase between the two nucleus. So only positive overlap, intermixing of positive phase with positive phase results in high amplitude, high value of wave function. High magnitude of wave function results in high value of the square of the wave function, high probability of finding electron between the two nuclei. आ रहा समझ में सौम्या? So therefore, only positive overlap results in bond formation. Negative overlap does not result in any bond formation. Overlaps involving d orbitals. Suppose z axis is internuclear axis. Suppose, okay, dz plus dz square will give sigma 1. कैसे ध्यान से देखो, this is a pz orbital. थोड़ा थोड़ा बना लेता हूँ. dz square orbital. dz square कुछ ऐसा आता है. They should be in the same phase. It results in a sigma bond. आ रहा समझ में? समझा? ये कौन क्या क्या बोल रहा है वीरो? व्हाट कौन आर यू टॉकिंग अबाउट? नहीं नहीं, कोई कौन वोन नहीं है. एक कोनिकल नोडल सरफेस बनता है, बट वी आर नॉट टॉकिंग अबाउट द नोडल सरफेस हियर. dz स्क्वायर का शेप हम बोलते हैं, देयर आर 3 लोब्स इन dz स्क्वायर. तो 2 लोब तो p ऑर्बिटल की तरह ही है, pz की तरह है, और एक डम डोनट शेपेड लोब होता है जो सर्कुलर रिंग जैसा है, उसको डोनट शेपेड लोब होता है. ठीक है, तो pz and dz square will give sigma bond. Next देखो, z axis is the internuclear axis ना, z axis is the internuclear axis. We can have dxz. This is a dxz orbital and another dxz orbital. dxz plus dxz will give a pi bond. It's a two lobe overlap. ध्यान से देखना. Positive, negative, positive, negative, positive, negative, positive, negative. It's a two lobe overlap. It's a pi bond. Overlapping is on the either side of the internuclear axis. Internuclear axis के ऊपर overlap है, internuclear axis के नीचे overlap. यहाँ पे देखो, it's a one lobe overlap. It's a two lobe overlap. आ रहा है समझ में? We were talking about overlaps involving d orbitals. एक pz dz square का देखा हमने, एक dxz और dxz का देखा. Similarly, dxz and px. About, because z axis is the internuclear axis, px will be perpendicular to it. This also results in a two lobe overlap, resulting in formation of a pi bond. So this also results in a pi bond. Similarly, dyz and py will also result in formation of a pi bond. आ रहा है समझ में ये? नेक्स्ट देखो, overlap between dxy and dxy. This results in a new bond which is called a delta bond. It is formed by 4-lobe overlap. Similarly, with z-axis as the internuclear axis, dx square minus y square plus dx square minus y square will also form a delta bond, which is because of a 4-lobe overlap. अभी तक हमने जो overlaps किए हैं 2-lobe overlap या 1-lobe overlap किया है, ठीक है? 1-lobe overlap results in formation of sigma bond, 2-lobe overlap results in formation of a pi bond, a 4-lobe overlap results in formation of a delta bond. थोड़ा difficult है draw करना. Think of two parallel faces of a cube. Think of two parallel faces of a cube. ठीक है? एक फेस को मैंने एक डिफरेंट कलर से रिप्रेजेंट कर दिया. We have one orbital. एक सेकेंड, थोड़ा और बड़ा बनाने दे. ठीक है? We'll have 1d orbitals like this. And another d orbital on the other face of the cube. आ रहा है समझ में? ये दो d orbitals दिख रहे हैं, दो अलग अलग एटम्स के d orbitals हैं, और एक्सिस ये वाला एक्सिस है, इंटरन्यूक्लियर एक्सिस. एक सेकेंड. It is passing through center of the two faces. This is the internuclear axis. ये जो इंटरन्यूक्लियर एक्सिस है इसको मैंने z एक्सिस ले लिया, ऐसा z एक्सिस है. सपोज ऊपर है x एक्सिस और इधर है y एक्सिस. आ रहा है समझ में? सार्थक मैं वही एक्सप्लेन कर रहा हूँ, डेल्टा ओवरलैप ही एक्सप्लेन करने की कोशिश कर रहा हूँ. तो वी आर कंसिडरिंग टू पैरेलल फेसेस ऑफ अ क्यूब. ये जो येलो में ड्रॉ किया उसको सामने की तरफ एज्यूम करो और जो व्हाइट में ड्रॉ किया वो पीछे की तरफ है. तो ऐसे दो पैरेलल फेसेस पे दो डी ऑर्बिटल्स बनाए मैंने. पहले ये समझ लेते हैं विरोक, पहले ये वाला समझ लेते हैं फिर तुम्हारा डाउट एक्सप्लेन करूंगा. अभी ध्यान से देखो, ओवरलैप इज बिटवीन 4 डिफरेंट लोब्स. ये और ये लोब ओवरलैप करेगा, ये इससे ओवरलैप करेगा, ये इससे ओवरलैप करेगा, ये इससे ओवरलैप करेगा. तो 4 लोब ओवरलैप है ये. दिस इज अ 4 लोब ओवरलैप. The phases can be written as positive, positive, negative, negative, which is a 4 lobe overlap. आ रहा है समझ में क्या सार्थक? A little bit of 3D visualization is required to understand this overlap. Okay. Similarly, if x-axis is internuclear axis, then dyz plus dyz will give delta overlap. dxy plus dxy will give delta overlap, delta bond. dxy plus dxy will give pi bond, and dxz plus dxz will give pi bond. Px plus dx square minus y square gives sigma bond. Ez plus dxz gives pi bond. Py plus dxy also gives pi bond. ठीक है, हो जाएगा. ये समझ में आ रहा है? ये विरोक आ रहा है समझ में? सौम्या एक सेकंड रुकना.
Now let us understand the orbital overlaps in some molecules. Let us consider F2 molecule. Okay, fluorine atom is 2s2 to p5. It has only one half-filled orbital. It is the half-filled orbitals that will take part in bond formation. So, दो फ्लोरीन एटम्स लेंगे और दोनों फ्लोरीन एटम्स के हाफ-filled orbitals ओवरलैप करके बॉन्ड फॉर्म करेंगे. Half-filled orbital of one fluorine atom will overlap with half-filled orbital of another fluorine atom, resulting in bond formation. Overlap of two half-filled orbitals. Conventionally, we consider z-axis to be the internuclear axis. Nothing is specified. We assume z-axis to be the internuclear axis. ये point add कर लो. Conventionally, z-axis is taken as the internuclear axis. ठीक है, तो यहाँ पे we'll have overlap of pz orbital with another pz orbital. So one pz orbital overlaps with another pz orbital, resulting in formation of a sigma bond. So in the F2 molecule, we have a single bond that is a sigma bond. We have one bond pair and three lone pair on each fluorine atom. The bond pair is formed due to an axial overlap, and it is a sigma bond. आ रहा समझ में? Now considering the O2 molecule. O2 molecule oxygen atom configuration is 2s2 to p4. 2s2 to p4 अगर draw करेंगे, there will be two half-filled orbitals. This is 2s2 to p4. दो oxygen atom side by side draw कर लो. Both of them have two half-filled orbitals. Half-filled orbital of one will overlap with half-filled orbital of another to form bonds. So this is one oxygen atom. This is another oxygen atom. Suppose ये px है, ये py है, ये pz है. So pz and pz overlap to form a bond. py and py overlap to form another bond. ठीक है, pz और pz का overlap से क्या bond बनेगा? Sigma bond, क्योंकि z axis is the internuclear axis. py और py के overlap से क्या बनेगा? Pi bond बनेगा. तो in O2 molecule there is a double bond between two oxygen atoms. उस double bond में एक bond sigma bond आएगा, एक bond pi bond आएगा. ठीक है, ये जल्दी से नोट कर लो. ये प्रीवियस पेज जल्दी से देखो एक बार. देखो, once overlapping has taken place, electrons will get paired, and paired electrons must have opposite. ये तो criteria of overlap में लिखाया था मैंने सौम्या. Overlapping orbitals must be half filled and contain electrons of opposite spin. नेक्स्ट देखो, O2 molecule में there is one overlap between PZ and PZ, another overlap between PY and PY. तो simultaneously दो ओवरलैप्स हो रहे हैं, एक सिग्मा ओवरलैप, एक एक्सियल ओवरलैप और एक लैटरल ओवरलैप. दोनों को साइमल्टेनियसली कुछ ऐसे रिप्रेजेंट करते हैं. This is the axial overlap between PZ and PZ and another overlap between PY and PY. There will be two lobe overlap. एक नीचे वाला lobe overlap करेगा, एक ऊपर वाला lobe overlap करेगा, resulting in formation of a pi bond. In a O2 molecule, there is a double bond, and this double bond has one sigma bond and one pi bond. In the double bond, one bond is formed by axial overlap, one bond is formed by lateral overlap. Similarly, let us consider the N2 molecule. Nitrogen is 2s2 2p5, 2s2 2p3, 2s2 2p3 देखेंगे तो nitrogen has three half-filled orbitals. So half-filled orbitals of one nitrogen atom overlap with half-filled orbitals of the other nitrogen atom. Resulting in three overlaps, three bonds. अभी PZ का axial overlap आएगा, resulting in formation of a sigma bond. PY will give lateral overlap. PX is also perpendicular to it, will also give lateral overlap. आ रहा समझ में? Suppose ये PZ है, this is PY, this is PX. N2 molecule has a triple bond. In the triple bond, we have one sigma and two pi bonds. So an important point you can conclude from here is single bond is a sigma bond. Double bond has one sigma bond and one pi bond. And triple bond has 1 sigma bond and 2 pi bonds. Okay, so we can use this result to count the number of sigma and pi bonds in different molecules. Okay, next देखो. Let us count number of sigma and pi bonds in some molecules. Find the number of sigma and pi bonds in each of the following. HCN. HCN has this structure. There is one triple bond. Triple bond will have 2 pi bonds. And there are 2 sigma bonds also. A carbon hydrogen sigma bond, a carbon nitrogen sigma bond. It has 2 sigma, 2 pi. Total bonds count करना है. एक hydrogen carbon sigma bond, एक carbon nitrogen sigma bond, and 2 carbon nitrogen pi bonds. ठीक है? Suppose we are talking about CH3CHO. CH3CHO, if you observe closely, ऐसा structure आएगा. How many sigma bonds? So 1, 2, 3, 4, 5, 6 sigma bonds, 1 pi bond. आ रहा है समझ में ये? Second one is ethanol. तो previous page देख लो जल्दी से. Next देखो. C2CN whole 4. C2CN4 can be understood to be derived from C2H4. Carbon double bond carbon, and each carbon bonded to 2 cyanide groups. Count करो number of sigma and number of pi bonds. It has 9 sigma and 9 pi bonds. एक और देख लो. Let us consider benzene molecule. This is the benzene molecule. Short में ऐसे represent करते हैं, but it has hydrogen atoms on each carbon. Each carbon has hydrogen atoms. So when we count sigma and pi bonds, we'll also count the carbon hydrogen sigma bonds. Effectively, it will have a total of 12 sigma and 3 pi bonds. आ रहा है समझ में? पेज टर्न करूं? Next, we'll study about hybridization. Why do we need the concept of hybridization? पहले ये explain करते हैं. To understand this, let us study bonds with the help of VBT, okay, in a polyatomic molecule. एक एग्जाम्पल करते हैं, फिर उससे क्लैरिटी आएगी. तो पहले मैं लिख देता हूं. It is needed to explain it is required to explain the structure of molecules of polyatomic molecules such as CH4, NH3, etc. Let us try and apply VBT in CH4 and look at limitations of VBT in CH4. Okay. Carbon has configuration of 2s2, 2p2. 2s2, 2p2, it has only two half-filled orbitals. Has only two half-filled orbitals, can form only two bonds. Hence, can form only two bonds in its ground state. Ground state means the lowest energy state. This is ground state electronic configuration of carbon. In the excited state, an electron from 2s can be excited to 2p. This is carbon in the excited state, 2s1, 2p3. Now carbon has four half-filled orbitals. It can form four covalent bonds. The first important point is, in CH4, bonds must have been formed in the excited state of carbon. In the ground state of carbon, we'll have only two half-filled orbitals on carbon. Carbon can form bonds with only two hydrogen atoms. But in the excited state, when one electron from 2s is excited to 2p, carbon now has four half-filled orbitals. It can form four covalent bonds with four hydrogen atoms. आ रहा है समझ में? Think of the hydrogen atom. All hydrogen atoms have 1s1 configuration. So all the four hydrogen atoms have one half-filled orbital. All the four hydrogen atoms have one half-filled orbital. So how the bonds will be formed? Half-filled orbital of carbon will overlap with half-filled orbital of hydrogen atom. This is how bonds will be formed. Half-filled orbital of carbon will overlap with half-filled orbital of hydrogen. Okay. 2-3 minute रुक जाना. Let me finish this. तो CH4 मॉलिक्यूल के फॉर्मेशन को हम कुछ ऐसे रिप्रेजेंट करेंगे. The excited state of carbon, and we have four different hydrogen atoms, all having one electron in their 1s orbital. Four different hydrogen atoms. So there will be overlaps between the half-filled orbitals of carbon and half-filled orbitals of hydrogen. So out of the four, one CH bond is formed due to SS overlap. Two S of carbon and one S of hydrogen. Other three CH bonds are formed due to sp overlap. Two p of carbon and 1s of hydrogen. Now we have studied earlier that stronger three CH bond should be stronger than the remaining one CH bond. Also, the three CH bonds formed due to sp overlap should be perpendicular to each other. Why? One overlap is with px, one overlap is with py, one overlap is with pz, and the three p orbitals are perpendicular to each other. Okay? Therefore, the three bonds must be perpendicular to each other. As the three p orbitals are perpendicular to each other, okay? So when we apply valence bond theory on CH4 molecule, what do we get? We get that the CH bonds must be perpendicular. And there are two types of carbon-hydrogen bonds. There should be two types of, as per VBT, there should be two types of carbon-hydrogen bond. Three bonds are stronger and one bonds are weaker. But on experimental study of CH4 molecule, it has been reported that all the carbon-hydrogen bonds in CH4 molecule are of equal strength. All the CH bonds are equally strong. Okay, and all the carbon-hydrogen bonds are oriented not at 90 degrees to each other, but an angle of 109 degrees to each other, which results in a tetrahedral orientation. So these 2 points cannot be explained on the basis of valence bond theory. Hence, there's the need of a different concept or some modification in the valence bond theory to understand completely the structure of CH4 molecule. Okay. We'll write this point. These contradict the experimental observations about CH4 molecule. इसको next page में लिख देता हूँ मैं ये point. But actually, all the carbon-hydrogen bonds in CH4 are identical. And are oriented in a tetrahedral direction. And have a tetrahedral orientation. The next lecture में मैं वापस explain करता हूँ. And have a tetrahedral orientation. Not perpendicular to each other, are at are at tetrahedral orientation, are at angles of 109 degree 28 minutes. Okay. This cannot be explained with the help of valence bond theory. Hybridization, the concept of hybridization was required to explain these points in CH4 and many other molecules. Hybridization क्या है ये next lecture में मैं पढ़ाऊंगा, तो अभी के लिए बस इतना point लिख लो. The concept of hybridization was introduced to explain such anomalies in CH4 and many other molecules. ठीक है, तो वैलेंस बॉन्ड थ्योरी का कंसेप्ट अप्लाई करेंगे CH4 पे, तो विल गेट 3 कार्बन हाइड्रोजन बॉन्ड्स as stronger formed due to sp overlap, 1 कार्बन हाइड्रोजन बॉन्ड as weaker formed by ss overlap. ठीक है, s ऑर्बिटल्स आर नॉन डायरेक्शनल, तो ss ओवरलैप से जो बॉन्ड बन रहा है उसका हम एंगल डिफाइन नहीं कर पाएंगे, but the 3 overlaps formed due to sp overlap, the 3 bonds formed due to sp overlaps will be perpendicular. As per valence bond theory, 3 bonds should be stronger, 1 bond should be weaker, 3 bonds should be perpendicular to each other. But experimentally, actually, the bond angles in CH4 molecule are found to be 109 degree 28 minutes, and all bonds are found to be equivalent, equally strong. Thus, the results obtained from valence bond theory, there are anomalies. VBT results in some anomalous nature in the CH4 molecule. These anomalies मतलब different from the expected behavior. तो VBT से कुछ और आ रहा है और experimentally कुछ और आ रहा है. तो VBT cannot explain the complete structure of CH4 molecule. So thus, not only in CH4, there are many other molecules in which VBT fails or fails to explain the structure completely. In such molecules, we need the concept, a new concept, and that was used to explain the concept of explain these anomalies, explain the shapes of polyatomic molecules such as CH4. तो आज के लेक्चर में हम इतना ही करते हैं. ठीक है, तुम लोग VBT तक का फाउंडेशन बिल्डर्स ऑब्जेक्टिव कंप्लीट करो, ज्यादा नहीं है. FBO में क्वेश्चन
up to 21. ठीक है, कंप्लीट करो. ठीक है, बाकी नेक्स्ट टाइम कंटिन्यू करते हैं. चलो, थैंक यू.